it just compound interest is actually a concept that is going to kind of filter into the next several sections. When we look at our compound interest formula that we talked about yesterday, just let me double check to make sure this is recording from the right thing. Okay. We said yesterday, we worked through the kind of the proof of this formula. We said A of t, where t is in years, is equal to your principal, okay, which is your initial amount, times 1 plus your interest rate divided by the number of compounds. So that will tell me kind of the portion of my interest rate that I earn on each compound. And then we arrange it to the nt, the number of compounds times the duration that my principal was within this account. That's our compound interest formula, okay? We're going to continue to use it, like I said, over the next several sections, but in the next several sections, the questions that will be asked will be more aligned with finding out what t is instead of finding out what A of t is. Does that make sense? Okay. A of t, very easy to find out algebraically because they're going to give you the p, they'll give you the principal, they'll give you the interest rate, and they'll give you the number of compounds. And they'll give you the time. They'll give you those 4 variables. And you just plug them in and evaluate it. Okay? It's like ninth grade algebra. Tomorrow on the next day, the question will be, okay, here's the principal, here's your interest rate, here's your number of compounds, and you want at some time to have in this account maybe $30,000, use logarithms to solve for the time that this money has to sit in the account so that you earn $30,000. Does that make sense? Okay. So it's just kind of the compound interest is a tool that we use, it's a concept that we use to allow us to kind of investigate different style or different kind of techniques algebraically. Okay. We'll be solving for the variable in an exponential equation. And we have these logarithms to do that, and this is one of the kind of, essential formulas that we use to provide story problems to be able to do that, okay? Other ones are like half-life. We talk about, you guys know what decibels are, okay? The scale of loudness, right? Okay? That is a logarithmic scale. The intensity of, we talked about this the other day, intensity of like earthquakes and pH scale, those things are all logarithmic scales, so we'll use logarithms to help us kind of solve for the exponential, okay, or the variable that is in the exponent. So we're going to see this, okay, so even though we've only done a couple examples so far, it will be played over and over and over again, hopefully we pick up on it. One of your questions at the end of yesterday's homework introduced this idea of what we call present value. So they define it maybe a little bit differently than what I'm writing here, but it says present value is the principal P in which you need to invest right now so that you have a desired amount later on, okay, after so many years or whatever, okay? So that's what present value means. Essentially, it's telling you through one vocabulary word that we're going to be looking for what we need to invest, okay? If I'm getting ready for retirement or preparing for retirement or something like that, and I've got this savings account that I'm putting money into or funneling money into, and I know the interest rate on it, I know how many times it gets compounded, and I know that I plan on when I retire of living maybe 20 more years, and I know that I want to live off of maybe $5,000 a month, I could say, okay, this is how much money I need when I retire. Does that make sense? Okay, and we can use this idea, okay, if that's how much money I need at the moment I retire, what do I need to invest now so that I can get there? Okay, you see an example here that says I want to purchase a boat, a $25,000 boat, okay, and I'm planning on doing that in 60 months, okay. I don't want to finance this thing. Okay? I think it's very important that you guys as 17, 18, 19-year-old students understand what financing an object means. I want to finance a car. Okay? Obviously, the better credit score you have, the better interest rate you're going to get, and obviously that means lesser overall investment. But understand, when you see a sticker price on a car, that's not what you're paying. You guys know that? Okay? You're going to finance it. You're going to pay an interest rate. I'm not sure what car interest rates are right now. But if the sticker is $25,000, I might be paying like $32,000 when it's all said and done. Okay? When I buy a home, okay, you've got options on homes. You have all kinds of different loans. You got conventional loans, FHA loans. You have balloon loans. And those are all things that you're going to want to investigate when you purchase a home and be careful with them. You have loans that the interest rate will start off being low, like a 0.5 interest rate. But at the end of the loan, it's called a balloon loan. At the end of the loan, that interest rate might be 15%, okay, which will shock the crap out of you someday. So usually when you apply for a loan, you want to think about your economic standing at that point. Okay, I don't want to go get a, because I might not have a lot of money right now in my savings. I don't want to get a balloon rate loan, even though it's lucrative, because at the beginning it's a very, very low interest rate, and I'm not paying a whole lot on my payments. But a balloon's at the end, and I find out that I'm paying like 5 or 6 times my initial payment at the end of the loan. Okay, that might be kind of shocking. Does that make sense? Okay, some balloon loans, you might have like on a mortgage, you might start off paying, I don't know, let's say $1,000 a month on your mortgage. Okay, at the end of that loan, the balloon rate, you might be paying $7,000 a month on your mortgage. If you don't have an income that's generating you $7,000 a month, that's going to be a problem, isn't it? Okay, so those are things you want to think about, because understand what banks do. Banks are a business, right? They're going to try to make money off you, regardless of whether that's positive or negative for you. So they might try to sell you a balloon rate loan because right now it looks beneficial to you. But down the road, maybe not a good idea. Maybe if you're a person that says, okay, I have very, very low income right now. I would really like a really, really low interest rate. But I know that in 5 years, I've got an aunt that is dying. She's leaving me so much money. I can afford a balloon rate loan 5 years from now. Does that make sense? Okay? Just a hypothetical. I don't know. But if you're going to come into money at some point, maybe that is something that you could use. But just going back to like a conventional loan, you got 15 years, 30-year options to pay off a conventional loan. If I go like a 30-year route, which is pretty common, if you have like $200,000 home, after like interest rate for 30 years, you actually out of pocket pay like $400,000. Okay, you pay double of what your home was initially worth. Okay, or what they said it was worth. The market value was. Now, a 15-year loan is obviously going to reduce that a little bit, and making more payments. A larger payment off your principal every month will reduce that. But what the sticker price is not what you end up paying. I don't want to pay extra for my boat. I want to pay for that thing with cash, okay? Because that means when sticker price is cash, paying $25,000, that's all I ever have to pay for it, right? Well, I don't have $25,000 right now, but I know that I have X amount of dollars. Maybe I'm close to that. I want to invest that money so that in 60 months when I need my boat, I have that money. Does that make sense? So just going to figure out how much I need to invest now. So in 60 months, my amount after 60 months, so A of T, that's a variable, I want that to be $25,000. I think a lot of people, when they see equations like this or formulas, they forget that the thing that we have this solved for, A of T, that is a variable. Okay, so $25,000. My principal, that's what we're looking for. That's what I want to invest. 1 plus my interest rate. Interest rate is 4.25%. So move that decimal over 2 spots. I'm going to compound it now. It says bi-weekly. What's bi-weekly mean? Every 2 weeks. So if I'm doing this on a year, because remember when we talk about compound interest, T is always in years. So when I see bi-weekly, it's always got to be what that means for a year. What's it mean for a year? 26. Okay. My interest, or sorry, my compounding it into the T or in times T would be 26. Now T was 60 months. What is T always in though? Years. So what do I got to change that to? 5. Okay. So I'm going to have that. Now, do I have the ability to solve for P then? Yeah, because this P and this garbage here, this is just one number, right? That's a coefficient essentially for P. So I can divide both sides by that and get P. So 25,000 divided by 1 plus 0.0425, or 26, raised to 26 times 5. That should give you the P value. If you're going to use your calculator, that's awesome. Go ahead. I like to use Desmos with these, and or at least show students and try to prod you to use Desmos, because when I type it in, that looks like how I wrote it, right? And that's going to be the safest thing for us when we're writing these, or trying to evaluate these. When I type this one in, it comes out to $20,217.51. That's what I need to invest today. So that 5 years from today, I can pull out $25,000 into that account. Does that make sense? So it's not nice. It makes $4,800 from it, right? Just sitting there. Yeah, I just wrote it down. So it'd be 45. So that's what I would invest today, so that I can pay with cash $25,000. Okay. Now $20,000 is still a lot of money, right? Okay. But maybe I have that. Maybe my issue is that extra $4,800 and I can't figure out how to get it invested. Okay. And if you have a savings account, okay, a lot of people have like a little nest egg in their savings account for like a rainy day, for something that's bad. Maybe like an automobile needs repaired. Maybe you have a something with your house that has an issue, that you have a large amount of a heater, or furnace goes out, or air conditioner goes out. Those are large costs, one-time payments almost, that people kind of save in their bank accounts. Okay. Well, if you have, say, $20,000 in your bank account, your savings account, okay, it's stupid just to let that sit there if you know that you'll never at any one time need that $20,000. Does that make sense? Okay. Take out, so put in that savings account maybe like $5,000. Okay, maybe that's a good little nest egg in case you have maybe a bad week and some appliances just take a dive in your house, and maybe you need some car repair or something like that. So $5,000 sitting in your savings account. Now you take that $15,000, you can invest it, and when it's sitting there invested in an account, it's making you money. Does that make sense? Where if it's just sitting in my savings account, it's not making me anything. Okay? Savings accounts do have a return on them, but they're like less than 0.5%. That's stupid. Like every year that we get our savings, every year that your bank will send what you earned off your savings account. Yeah, like it's stupid small. It's like pennies on the dollar. Okay? Not even pennies on the dollar. It's like you could have thousands of dollars in there, and you're gonna make like $4. It's stupid. Okay. And you can look online. You can do a quick Google search of a bank and say, okay, what is your interest rate on your savings accounts? Okay. You can go to a financial advisor, and they can give you like ideas of. There are things called money markets where you invest your money that way, and they're essentially savings accounts, but there's risk involved in some of those. But a money market will offer upwards of like 2.5% return, which is pretty good. But at the same time, there's risk in that, because you could lose in a money market. The way some of them are set up, you could lose your initial investment. Okay. All right, so that brings us to talking about the natural exponential function. Okay, we talked about this the other day a little bit, but the bell rang. It's the number e. Okay, and I gave you a little bit of history. E is after, I guess what they argue is that, I don't know if there's any real true documentation on why it's the letter E, why we chose that symbol. But there was a guy named Jacob Bernoulli. He was interested in looking at compound interest, the same formula that we're interested in here. And he was looking at that 1 plus R over N raised to the NT. And he was interested in what happens as we start to compound over and over and over and over and over, and ultimately compound an infinite number of times. He was interested in what does that 1 plus R over N to the NT, what does that eventually tend to? What does it go to as that exponent essentially gets very, 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 very big, or the number of compounds gets very, 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 very big. And he came up that he used the idea of limits to do this, and he came up with that amount will tend to 2.7182825, something like that. He found out that it's going to tend to that number there. Okay. It basically, the way he did this is like I said, he used some numerical approaches. He was interested in essentially this formula. Okay, if you think about that, that's like our R over N raised to our NT. Okay. If I look at that and I'm interested in, let's put a point on here, and I'm going to ask it just to show me the Y value of point A. So we're getting this number right here. As I take that A and I start moving it, okay, look at the Y value. Oh, look at the Y value of A. It's slowly approaching that 2.718 number, right? Let me zoom out further so we can move it faster. So now that so now here to over 100, you see that 2.7, the 7, so this is the one that's changing, right? That 7 is now constant. Now look at this 0 here. That 0 is going to now change to a 1, right? Now look at that 0, as I move A. That's going to change. Okay, so it's at a 4 right now, 5. And now it's to get to that 8. Come on. Get to that 8, and now this becomes a 0, right? And it will increase to that 2. And then eventually this one will become a 0, and it will eventually increase to the 8. Does that make sense? So that's kind of what we call the an approximation technique. As we move out, we're seeing that these decimals, the further we move that A value out, or essentially the X, in that denominator and as that exponent, as that X starts getting larger and larger, we start to see that those decimal places are kind of determining themselves, and that 2.7 becomes constant, and then 2.718 becomes constant, and 2.7182 becomes constant the further I move out. Does that make sense? Now, as I keep moving out, it will be infinite decimal places that kind of keep showing that pattern. And we see that there is no pattern in regards to the quantities in those decimal spots, right? And it starts to look initially, I think, this starts to get people, kind of in this range here, start thinking that there might be a pattern there because you see a lot of 8 2s, right? But as we move on, or GeoGebra only does 15 decimal places, but as you move on, that thing does not end and it does not repeat. This is an irrational number, okay? Euler was interested, I believe he was interested in, I think he was approximating this thing. He approximated it without any technology out to like 18 decimal places. Okay? And I believe he was using like factorials to do that. Okay? But this Bernoulli guy was before him. There's a Napier guy in science with this stuff. He was before Euler, but those guys that were doing this work before him never really realized or classified or identified that number. Euler's work is kind of the first work that actually started to classify and define and identify that number. Does that make sense? So a lot of argument is said that the credit goes to him, but there was work being done prior to him with this stuff. Whether the people that were doing that work really realized what they were doing, and the relationships that exist in with this number. This number E ends up being very, very useful for us in calculus. Okay, it's going to be one of the primary bases that we use with logarithms. Okay, but it's just an irrational number, so we treat it like every other number that we ever come across. The one thing that I think scares people mathematically is they start to see symbols and they lose the realization that that symbol represents something. What does that symbol represent here? It represents a number. So I treat it just like any other number. Does that make sense? So if I had, for instance, 2 to the x, and I had 3 to the x, okay, and I put just the number 2 down, I put the number E down, and I put the number 3 down. So you see how E is between 2 and 3, and it's closer to 3, right? So then when I look at what the graph of E to the x looks like, the same kind of argument should kind of present itself, okay? I don't know if I can rearrange these. I can't. Let's do it this way. Nope, won't do it. So we got 2 to the x, you got 3 to the x, you got e to the x. So this is 2.718281828459045. In infinite decimal places raised to the x. Well, that's pretty similar to 3 to the x, pretty close to 3 to the x, right? So the behavior of that purple one should model the behavior of 3 to the x closely. Does that make sense? Okay. Now, if I just look at e to the x, everything that we talked about the other day should be constant, should be consistent, okay? Now my k value here, maybe I write this as 1 times e to the x, okay? But my k is just 1 here, right? But we talked about every single exponential will have the ordered pair 0, comma k times 1, right? Let's get that point. Every single exponential will have 1, comma k times the base. And every single exponential will have negative 1, comma k times 1 over the base. I should have those 3 points, right? So I have 0, comma 1, I have 1, comma e, and I have negative 1, comma 1 over e. That's the same as the information I would have done if I had the base being 2 or the base being 3 or whatever. Okay? Everybody kind of on the same page here? And I want to explain to you through the proof of a formula here in a little bit the benefit of E and knowing where it came from. All right. So the next couple of slides, guys, just kind of talk about that kind of investigation of 1 plus 1 over n raised to the n, or 1 plus 1 over x raised to the x. As n or x get really, really big, what that thing tends to, and it tends to that irrational number, e, right there. So then we start talking about, the fact that it's any other number, just like any other number, so we can use it as a base, like any other number. And we get this. This is a natural exponential function. Just f of x equals e to x. This is what we just graphed. It's exponential. It shows the exact same behavior as any other exponential. Has the same 3 points that any other exponential has, based off of that different base. So then it asks us to evaluate. So it just takes your calculator and starts plugging those things. I'm not going to do that with you. I think you guys can do that. We'll get to this, okay? And this is the idea in which we're interested in a science kind of model on how diseases spread, okay? A lot of times this might be referred to as a logistics model, okay? And it's the idea of how we can collect data to create essentially that model, okay? So data collection is helping us find VMT's equation. But then once we have that data, we can start to trying to interpret and analyze how this disease is spreading, how it has spread, how it started, that kind of thing. Okay, and you kind of put a case together in regards to this disease. What I want you to understand is that some diseases, depending on the size of the population, some diseases will annihilate, decimate, destroy the entire population. Okay. In the news lately, there was a guy who was trying to spread Christianity to one of the last kind of indigenous tribes of the world. It's on an island in the Indian Ocean. You guys see this? Okay, he kayaked. He got through like the Indian government Navy on a kayak and got on shore. And this tribe of like 200 people that had actually no contact with the outside world shot him with bows and arrows, killed him, and now his family wants to go get his body. The governments are saying, no, you can't go. Nobody's going to go get his body because somebody with a common cold could put that bacteria or virus on that island, and those people have never had any outside contact. Maybe once or twice with, if you've read any history about it, there was a guy like 30 years ago that would like take stuff to them, but they never let him like off his boat. They have had very limited contact, so they don't have an immune system, right? It's like how the Native Americans, when the English first got here, okay, they didn't have an immune system to those diseases, so it decimated those populations, right? The Aztec, Incas, those types of populations decimated because of things like smallpox and those diseases. So the idea is that those populations were not big enough to kind of suppress that virus, okay, or those diseases. This disease here, we'll see that the population is actually, based off this logistics model, is big enough to suppress that. This will not annihilate the entire population. Does that make sense? And that's kind of how things work, how the science works, how the virus works. Okay, eventually things, your immunity, the population's immunity, will eventually battle that virus. Does that make sense? Okay. So it says an infectious disease begins to spread in a small city, a population of 10,000. After 2 days, the number of people who succumb to the virus is modeled by the function that. Okay. So how many people are initially infected? Okay. So this would allow us to kind of pinpoint maybe a group of people and see, okay, this is how many people started this virus or allowed this virus to spread. And then maybe we can start to kind of analyze like where those people were from, what they were doing, that kind of stuff, okay, if we have maybe some more information. So basically all we've got to do, we see initial. Initial means what? Time is always what with initial? 0. So we got e to the negative 0.97 times 0, which that's just e to the 0. What's e to the 0? 1. So I've really got 10,000 divided by 1250. All right, so if I divide that out, it gives you 8. Okay, so we figured out now that 8 people were initially infected with this virus. Does that make sense? With this disease, yes. And now their interactions within this population of 10,000 people has created the spread of this disease and ultimately then this model. Okay, so the question then arises. How many people are infected after 1 day, 2 days, 5 days, and so forth? I think the best thing for you guys to do, if you're going to use I would use a TIA 384. I'll show you how to do it in Desmos as well. But I would type in my function here. Okay, now just be careful the way you type it because your denominator is a quantity, so you need those parentheses right there and right there. And your exponent is a product. If I don't put my e to the whatever in parentheses, then it will take e to the negative 0.97. Evaluate that and then multiply that by x, and I don't want that to happen, right? So I gotta have that in parentheses as well. But then I'll just go to my table. I'll go to second table, and now I can see my table is set up as integers here. If you don't have it set up as integers, you can go to second table set, and you say, okay, I want my table to start like maybe at 0, I want my change in table to be 1. That will be then start at 0, go to 1, go to 2, go to 3, go to 4. Then I go back to my table, and you see it starts at 0. So then I would find 8 when I did 0. 1 day, it'll be 20 people. 2 days, it'll be 54 people. 3 days, it'll be 137 people. Okay? But now as I move on, okay, after 10 days, I'm up to 1969. Okay? Keep going, though. What do you see then, eventually? It max out, right? Okay, it plateaus. It's exponential. That's going to happen. Okay? So the population was big enough for us to see that we do indeed have a situation where the entire population is not going to be annihilated by that disease. If you're going to use Desmos, this is a way to do that. We had 10,000 divided by, what was it, 1245 plus E raised to the negative 0.97. Now we'll put T, and it asks me to add a slider for T. And now you can see that when T is 0, you get that 8, right? Or is that 0.9? Is that
5 plus 4.5?
Man, I messed that all up. My apologies. So 5. There we go. There we go. All right. So now with T being 0, you can see that you got 8. Now if I slide T to be 1, there's your 20.966. Slide it to be 2. You got that. Maybe you want 2.5 days. You can have that. Does that kind of make sense? Okay, so if you want to use that tool on Desmos, you can by all means do that. So everybody like that? Okay. We see that a lot of like population, like interactions, like things like called predator-prey models, where I have like foxes and rabbits in the same population or same kind of environment, and I know there are two populations, how the size of one population can impact another one. Exponential equations like that one we just saw with diseases are very useful for us to, as biologists and conservationists, to kind of understand how those two populations interact. Does that make sense? Okay. More foxes I have, probably the less rabbits I have, right? The more rabbits I have, probably the more foxes I have. The less grass I have, the less rabbits I have, the less foxes I have, right? So analyzing as a biologist all of those interactions mathematically can allow us maybe to make valid conservation decisions. Okay? I don't know what's called, but the kind of wildlife, the DNR, okay, would probably, when they make, if you go buy like a fishing license, okay, there's limits, right, on what I can catch and keep, okay. Those limits are based on the sizes of those populations, right? Okay, if I go fishing for walleye, I might only be able to catch 6 of them in a day. If I go catch perch, I can catch 30 in a day. Well, how do they set those limits? It's on the size of the populations. You'd probably venture to say that the perch population is a lot bigger than the walleye population in Lake Erie, right? Well, how do they do that kind of stuff? How do they make those limits? They understand these logistical models that incorporate this natural number and analyze them and say, okay, these are, how we can reduce those populations and still have a healthy population, okay? So if you have interest in being a conservationist or a biologist or something like that, and you're good at math, maybe that's something that's out there for you. Okay, I want to talk in the next 10 minutes about a new formula. We have A of t is equal to P times 1 plus R over N raised to the NT, right? That's our compound interest formula if we're compounding monthly, weekly, bi-weekly, annually, semi-annually, that kind of thing. When we see a word that associates with it a number, right? Bi-weekly associates 26, monthly associates 12. The word continuous associates an idea. Continuous associates the word infinity. Does that make sense? Okay? Meaning that when my money is in this account, and after it compounded monthly, I have to wait an entire month before my initial investment earns me money, right? Where if it's continuous, the instant that it earns money, that money is then rolled over. Does that make sense? So the instant I earn any dividend, that gets reinvested as a principal, and now it starts earning money. So it's happening kind of it's way beyond this, way earlier than, let's just say nanosecond. Every nanosecond, my principal is being readjusted and reinvested. Does that make sense? So I'm earning money on top of money on top of money on the instant. Okay? So we're going to come up with a formula for this, because what happens is essentially your compounds are becoming infinite, right? Well, if I have infinity as one of my input values, I have r divided by infinity, and then I'm going to have raised to the infinity times t. That's a algebraic arithmetic problem. Okay, I cannot do that. All right, evaluate that. So we're really going to investigate this in a algebraic. If I take, I'm just going to do some manipulation here. I'm going to take this 1 plus r to the n. I'm going to rewrite it this way. 1 plus r to the n raised to the n divided by r. And then I'm going to raise that to the RT. Okay. Now my question is the red statement different from the black one, or the black one different from the red one? And your answer to that should be something algebraic. Your answer to that should be, well, what do I have here? I have a power raised to a power, right? What do you do with a power raised to a power? You multiply. So it's NR, because that's the only thing that's changed right here. This stuff here used to be NT, right? Is NR times RT still NT? Yes. Okay? So it's just kind of a convenient manipulation of this expression, and essentially this exponent, to get this. Now, why do I want to do that? Think about this. If I look at R over N, which is that thing right there, and I look at N over R, what are they to one another? And multiplicative inverses. So what's a word that we're more reciprocals, right? Look at this. Look at 1 plus 1 over x raised to the x. What is 1 over x and x to one another? Reciprocals. Okay? If I'm just going to make a substitution here. I'm going to say r over n. Well, let that be 1 over n. Okay, I can do that. If I have two variable values, r over n, I want to redefine that, whatever that quantity eventually becomes. I want to make it 1 over n. I want to just rename it. If that's 1 over m, and the idea of reciprocals isn't n over r, m, makes sense? Now, the reason I would do this is just to allow us to make a observation here that's a little bit easier than seeing it written this way. If I let r over n be 1 over m, and then n over r is m, and I raise that all to the RT, isn't this thing right here, and we say we're compounding continuously, right? Okay, so that m, that m is going to infinity in both spots, correct? Well, if we think about what we talked about at the beginning, I had 1 plus 1 over x raised to the x. As x went to infinity, what did this quantity tend to? What did it become? It became e. So doesn't this 1 plus 1 over m to the m, as my number of compounds go to infinity, doesn't that thing become e? So I'm left with my principal times e, and then I still have my RT. And that's how my formula changes when I take out the word weekly, bi-weekly, daily, and insert the word continuous. Okay? That 1 plus r over n to the n t becomes essentially e raised to, I guess, not the nt, so the 1 plus r to n raised to the n over r idea turns into e, and then I still have my exponent of rt. Is that all right? Where r is still your interest rate, t is still your time in years, and p is still your principal. So that is a continuous compound formula. Okay? And that's kind of what we call, we'll talk about it in a couple days, it is your growth rate formula, okay? If I have a bacteria that's growing at a particular rate, okay? Bacteria grows, it doesn't wait, it doesn't think about how bacteria works or viruses work and that kind of stuff, and cells divide and growth and all kind of thing. It doesn't wait for a 1 month to just kind of, at that 1 month interval, to just double its size, right? It's continuously growing. Does that make sense? Okay. So that's kind of the formula that we're going to see for all things that have exponential growth. A lot of times we don't use P, we use capital A sub 0, e to the RT. A sub 0 just means amount at time 0, right? Here we're using P because we're in the finance realms, so we think principal. Okay. So here's the question that you'll see. It's very similar to the question that we saw yesterday. I think it's actually using the exact same interest rate, time period, and principal. So if I go A of t is equal to principal E raised to RT, when I see the word continuous, that's an identifier that formula is what we're using. Okay? It says we want to invest $1,000. We want an interest rate of 0.12. And we're going to keep it in there for 3 years. If I go 1,000 times E raised to 0.36, E to the 0.36, $1,433.33, right? Okay. Now, that is the most that I can get by compounding that amount with that interest rate, okay? It will not go above that. Now, if I did, like yesterday, I think we did 365. It was pretty close to that, okay? But it was less than that. Continuous and compound something is always the best option. Does that make sense? So if I have, and I think there's several things going on here. Principal is obviously a component. Interest rate and time are obviously a component, right? And then the compound, how many times I'm compounding is another variable component. So if I am going to 2 different banks, and 2 different banks, one, let's say Chase and Superior. Let's say Chase says, we can give you 12%, we can give you 3 years, and you're going to invest $1,000. But Superior says, we can give you the exact same thing, but we cannot compound continuously, we're going to do it monthly. Who's better if Chase can go continuous? Chase. Marketing thing. Superior can't give me compounding continuous, but maybe they can give me a 12.05% interest rate. Does that make sense? So now what do I have to do as a consumer? I have to do the math. I have to be able to make a decision off that math, right? So I do the situation Chase is offering. I will do the situation that Superior is offering, see which one's the best, okay? Banks, they like to use interest rates as their marketer, okay? And people see that interest rate and say, oh, 3% is better than 2.9%. So that 2.9% might be compounded continuously, and it might be a better deal for you.
Does anyone actually compound continuously?
Yeah. I would venture to say I'd have to look up